In the last part of this unit, we would like to establish the continuity of the entropy function h of p as a function of p. At a high level, what continuity says is that if you change this distribution p from p to q, where q is close to p, then hp doesn't change too much. Okay, so we want to get some handle on the distance, the change in hp minus hq when p changes to q, and the change in p and q will be measured in terms of the total variation distance between p and q. Okay. So instead of just showing continuity in the sense that when dpq becomes small and this distance becomes small, we will give a more quantitative handle on this change, and we will uh, derive an upper bound for this change in terms of dpq, right? And that's what we would like to do. But once again, I would like to give you a slightly different proof of this fact, and in doing so, I'll use this excuse to introduce a very interesting result called the maximal coupling lemma, which is related to total variation distance. So what is the maximal coupling lemma? Let me just start with that part. The maximal coupling lemma. Earlier, we saw a variational expression, a variational formula for Kullback-Leibler divergence. Even before that, we have seen another variational formula for total variation distance. We saw that dpq can be expressed as max over all subsets A of x, probability of A minus probability of A under P minus probability of A under Q. This can also be viewed as a variational formula because it's max over A. In fact, there is another very interesting variational formula for total variation distance, and this is called this comes with the maximal coupling lemma. So let me describe what a coupling is and what is the maximal coupling lemma. So coupling, uh, coupling. Okay, let me make it more colorful. Coupling of two distributions P and Q on the same set X is a joint distribution Pxy. So it's a joint distribution of two random variables Pxy with X and Y taking values in this calligraphic set X. Okay, so X and Y both take value here. Px equals to P and Py, the marginal of Y, equals to Q. So this is what a coupling is. It's just a definition. So you call a joint distribution Pxy a coupling of P and Q if the X marginal of Pxy is P and Y marginal of Pxy is Q. So it's coming up with a fictitious joint distribution when you're given marginals, right? So any such joint distribution is called a coupling, and this, let me denote by pi p comma q as the set of all couplings pxy of p and q. Pxy is coupling of p and q. Alright, so this is the set of all couplings. The maximal coupling lemma, which is actually a result from optimal transport theory, it's a result of Strassen, maximal coupling lemma. So what this result says is that if I give you two distributions for distributions P and Q on the same set X, we have we have a nice formula for total variation distance. What this says, dpq, the total variation distance between p and q, is max over all couplings pxy. So pxy is a coupling of p and q. It's the max over all coupling probability that x equals to y. Okay, look for the say it's the maximal coupling. It has the minimum probability of error. So min over all couplings probability that x is not equal to 1. This coupling is a so what we are saying here is that we think of these couplings as somehow defining joint distribution, and maximal coupling is the one which maximizes the probability of x being equal to y, given that the marginals in p and q are p and q. And what this lemma says, the maximal coupling lemma says, is total variation distance is exactly equal to the minimum probability of error, the probability of error for the maximal coupling between x and y. This lemma actually has many applications. It comes in optimal transport theory, as I said. So you can think of two stations, one on this side and the other one on this side. So px, so both have values in this alphabet x. So px denotes the mass that you have at station x, and qx denotes the mass that you want at this receiving station x. Maybe I should call it y, at receiving station y. Okay, so these are the constraints. So you have this outgoing mass from this station, and you have this incoming mass at these stations. So station x must send at least px fraction of mass. Station y must receive at least qy fraction of mass. The question is, how should you send these? How should you deploy trucks to carry this mass from station x to station y? So you assign these mass to different trucks. Okay. With the constraint that the total mass leaving station x is px and the total mass coming into station y is qy. So how do you assign these masses? And what the maximal coupling lemma says. So what a coupling is this assignment, and what the maximal coupling lemma says is that so maximal coupling lemma actually gives a bound for some kind of mismatch in this assignment. So it can be interpreted in terms of this transportation cost. So let me be more precise here. So for each assignment, we associate with this assignment a cost. The cost that we associate is the indicator function x not equal to y, or x equals to y. So this is the cost that we are assigning. Basically, if you assign some mass on line joining x and y, the reward that you get is 0 unless x equals to y. Okay, and then this highest reward or highest cost, which is 1 minus reward, is attained by a particular coupling, which is the maximal coupling, and it is the highest cost. The least cost is given by dpq. That's the maximal coupling. Okay, this story is actually not related to our course, but I thought I'll give some background. However, this formula is very useful for us. So it gives yet another variational formula for total variation distance, but this time in terms of min, unlike a previous variational formula which was in terms of max. So let's look at a previous variational formula for dpq. This one here. This is the max over all subset A, and this new variational formula is in terms of min over all couplings. Okay. So I will not give a proof of this result, but I'll give you one side of the proof. Okay, so proof. What I'll show is that for every coupling pxy of x and y, of p and q, dpq is actually smaller than probability x not equal to y. Okay, that's what I'll show. And what I'm not showing is that in fact there is a coupling which can attain this DPQ. This construction has been rediscovered several times, but I think the first construction was due to Strassen, the one which attains this maximal coupling. Alright, so let's try to show this thing. Let's try to show this bound. So to show this, so this is what we want to show. So to show this, for any x, we note that px minus qx is equal to px, let me just px equals to probability that x equals to x and y is equal to x plus the probability that this is just a total probability formula, x equals to x, y is not equal to x. There was no real y in this definition of P. I just brought it out. This joint distribution was just designed through a coupling. Okay. And this guy here, probability that y equal to x and x equal to x, this is upper bounded by probability that y itself equals to x. Okay, because this event implies y equals to x. So this is some event. And whenever this happens, let's think of this event A, a bigger event B holds. Okay, so what is this B? This B is the event that y equals to x, and this is the event that x equals to x and y equals to random variable x. Okay, so this A event, which is this one, this is the probability we are looking at here, is contained in this B event. Okay, right? Plus this bound here, probability that x equals to x, y not equal to x. From this observation, it follows that px minus qx is less than equal to, I forgot one point. This probability here, probability that y equals to x, is just q of x. That's how our coupling is defined. Therefore, px minus qx for any x is less than equal to probability that x is equal to x and y is not equal to x. Okay. Therefore, when you sum over all x such that px is greater than qx and you sum px minus qx, that's exactly what total variation distance is. And this guy is less than equal to sum over all x, px greater than qx of probability x equal to x, y is not equal to x. Okay. Alright, so you have only summed over some partial set of x, but in fact that is less than equal to summing over all x. Probability that x equals to x and y is not equal to random variable x, and then by total probability formula, this is exactly equal to the probability that y is not equal to x. Okay, and so this is the proof that dpq is always less than this probability x not equal to y for any joint distribution xy with marginals of x and y being p and q respectively. What I haven't shown once again is that there is indeed a coupling which attains this bound, and in fact this proof contains the idea of that coupling. Essentially, you would like to construct a coupling where all these inequalities are tight. Okay, and yeah, so I'm not going through that argument, but so here is the result. dpq is min over all couplings probability that x is not equal to y. Okay, now using this maximal coupling lemma, what I would like to do is I would like to give you a proof, an estimate for how much entropy can change when you go from a distribution P to a distribution Q. And we'll use maximal coupling lemma in deriving this estimate. This is a very cool proof. Okay. Continuity of entropy. Okay, so here is my proof. So we want to control HP minus HQ. Okay, so consider a coupling PXY of P and Q. So HP minus HQ, P is the marginal of X, so that's HX, HP is HX, and Q is the marginal of Y, so that is HY. So HP minus HQ is exactly equal to HX minus HY, which is equal to H of X. Now, so this is the magic of the proof now. H of X minus H of XY actually is equal to, so some observation you can make, H of X given Y minus H of Y given X. How do you get this? You can pause and quickly show this. Okay, so I'm sure you were able to show it, but let me tell you the answer. You can just add and subtract H of XY, and then you will get this. Alright, so this is true. Now, this difference is also less than equal to max of H of X given Y and H of Y given X. That's true. You are subtracting something from this max and from one of these terms, and what you're subtracting is the other term, so you can never exceed this guy. So this is basically saying that mod of A minus B is less than equal to max of A and B for two non-negative numbers A and B. Okay, so that's some elementary inequality. Okay, so this is true. Now the question is, how do we bound this max? By the way, this looks like a very innocent step, but something magical has happened in this step. There was no joint distribution xy. We are free to choose any joint distribution xy we want, and this holds for all of them. Therefore, the best bound will be obtained by choosing the best joint distribution xy, which minimizes the right side above. And that's what we will do at the end. So, but before that, we have to figure out how do we bound these conditional entropies. Well, that's where our good old friend, Fano's inequality will help us. So the conditional entropy of x given y by Fano's inequality, so this is by Fano's inequality, is less than equal to, this conditional entropy is less than equal to probability that x is not equal to y. Actually, each of this term is less than equal to this. So the max is also less than equal to this. Log of cardinality of x minus 1 plus the binary entropy of probability x not equal to y. Okay. Okay. And but how do we go from here? Where is the total variation distance? Well, this is the point where you will choose your distribution, the joint distribution x not the joint distribution of x and y. You will choose the joint distribution of xy such that this probability that x not equal to y is equal to dpq. And as I said, this distribution can be found. The maximal coupling distribution can be found. Okay, so choose pxy, the coupling pxy, such that this probability x not equal to y is equal to dpq. So what do we have? So this guy here is just dpq log cardinality of x minus 1 plus the binary entropy of dpq. So what does that look like? dpq log 1 by dpq plus 1 minus dpq log 1 by 1 minus dpq. Okay, so this is the precise bound. This is the bound we were looking for. This is the bound for continuity of entropy. And we used a very nice maximal coupling construction to show this. Actually, I think this is the tightest known estimate for how much entropy will change when you change the distribution. So there are a few things to note here. This first term here is just proportional to dpq. If the second term was not here, this function will be called a Lipschitz function. Lipschitz functions are those for which fx minus fy are less than equal to a distance between x and y times some constant. The Lipschitz constant will be this guy. But this function is not Lipschitz. There is something here which is more than the linear term. It's not just dpq, it's dpq log 1 by dpq. Nonetheless, as dpq goes to 0, the second term, the binary entropy, the second term here is the binary entropy of dpq. The binary entropy of dpq. Some number dpq which is between 0 and 1. Total variation distance is always between 0 and 1. So as this total variation distance goes to 0, as distributions come closer to each other, this binary entropy goes to 0. Also the first term goes to 0, dpq itself goes to 0. This is some constant. This alphabet size is kept as constant. And therefore in the limit as dpq goes to 0, hp goes to hq, and therefore entropy is a continuous function of the probability p. In fact, we have shown a more precise estimate, it's what we have shown is that roughly the rate at which hp goes to hq as p goes to q in total variation distance is roughly some constant times dpq log 1 by dpq. And that constant depends on the alphabet size. It depends on the log of the alphabet size. Okay, that's the result here. Okay, this is the last property I wanted to show. I have tried my best to give you proofs which are not so readily available in the textbooks, although this is all standard material, but somehow these are more modern proofs than those that are available in the textbooks. So what we showed in this unit, the second unit on properties of information functions, is we first showed Fano's inequality, but we showed Fano's inequality using data processing inequality. Then next we showed some interesting variational formulae. We showed one variational formula for the Kullback-Leibler divergence, and another variational, so which is basically equivalent to what is known as Gibbs variational principle or Laplace integration formula. This formula is about 200 years old and has led to breakthrough in all kind of areas. Has led to breakthroughs in statistical physics, has led to breakthroughs in large deviation theory, and these days it is the one fueling something called GANs, and of course that is also sort of a breakthrough. So this formula is very nice. The other variational formula we saw was that for mutual information, which allows us to interpret the maximum mutual information that you can have between the input and the output of a channel, known as the capacity of the channel. So that maximum mutual information, capacity of the channel, this variational formula allows us to interpret that capacity as an information radius. Okay, that's what we did next. Then using this variational formula, we visited some applications. In particular, using this variational formula for Kullback-Leibler divergence, we were able to show Pinsker's inequality, which essentially says that the square of total variation distance is less than equal to some constant times Kullback-Leibler divergence. So Kullback-Leibler divergence behaves like square of total variation distance. Okay. And finally, we showed the fact that entropy is continuous in its argument, and we showed this using the maximal coupling lemma. So this is all I wanted to say in this unit. This was the second unit in properties of measures of information. So 6th unit and 7th unit are both about this. In the remaining lectures for this week, I'll switch to a different topic. What I will talk about is I will basically start my unit 8, which is on deriving lower bounds for different problems. So till now we saw entropy as some kind of answer to the compression problem or the randomness generation problem. We saw Kullback-Leibler divergence as an answer to the hypothesis testing problem, but we only showed one side of the bounds. We only showed some kind of a scheme which attains the performance related to entropy, but we never showed that this performance cannot be improved. And now in unit 8, we will show some matching lower bound for some of these problems. Okay, so see you in the next lecture.